Alrighty, so let me share my screen. Chat, who's that? Gladiator's working, yeah, okay. Share screen, this guy. Alrighty, so does anyone have any questions regarding the in-class assignment? Yes, ma'am. The third problem, alrighty. So we're gonna work the problem, but we're going to try to employ some of the techniques that we learned in these previous video lectures. And these examples more so are probably about the voltage division and current division than they are source combinations, although the first one can be solved using a lot of source combination as well. Alrighty, so before we jump into this, I want to show something or kind of explain something that I get frequent questions about. So the one that's leaving this voltage source has the current IS. And we should easily be able to see that that current IS flows through the 300 ohm resistor and then flows into the 15 kilo ohm resistor. Similarly, we could see that the current, since it left the source, it had to flow around this direction to be able to flow into the source as well. So if we performed Kirchhoff's current law, you can see that IS flows here as well, at this node, what would that tell us about the current? Let's call it just I right here flowing through that short. So we're performing Kirchhoff's current law at the node that I've circled in black. So what current enters? It's literally written on the picture. IS. What current leaves? IS plus I. So we have IS is equal to IS plus I. What does that tell us about I? I is, it has to be 0, right? In order for Kirchhoff's current law to be satisfied, the current flowing from left to right through that middle branch that's connecting the left-hand side of the circuit to the right-hand side of the circuit has to be 0. So this guy, even though there's no current, because there's no current flowing through it, we could treat it as if it were effectively an open circuit. What that line right there is really doing is telling us that the left-hand side of the circuit is coupled to the right-hand side of the circuit. And what I mean by that is that this voltage V pi on the left-hand portion of the circuit is the controlling voltage for this dependent source on the right-hand side. So we can treat it as if it were two completely separate circuits, except that this voltage makes this current source work, okay? So there's no current flowing through there that we need to account for, through this guy that we need to account for or anything like that. I'm just trying to show you that the stuff on the left-hand side influences the right-hand side, even if there's no current transfer across that short circuit. Alrighty, so all that talk about Kirchhoff's current law around the left-hand loop actually helps us a little bit as well, because we can see that that voltage source is connected to those two resistors, the 300 ohm resistor and the 15 kilo ohm resistors in series. So I have a known voltage drop over two resistors in series. That is prime pickings to use voltage division in order to solve for that voltage V pi without bothering to figure out what the current flowing around that left-hand loop is. So with that in mind, I can say that V pi, is equal to my source voltage, which is 3 sine 10t volts, multiplied by the resistance ratio. So in the numerator, I want the resistance that the voltage drop I'm interested in is occurring over, which in this case is the 15 kilo ohm resistor. And then I'm going to divide that by the total series resistance seen by the source, which is 300 ohms plus 15 kilo ohms. And in doing so, I can see that the voltage drop over the 15 kilo ohm resistor is 2.941 sine 10t. So that is voltage division at its most simple. We have a known voltage over multiple resistors, and we're interested in the voltage drop over one of those resistors. We can use voltage division to get that voltage simply by multiplying our known voltage times the ratio of the resistor we're interested in divided by the total series resistance. Alrighty, so now that we know what V pi is, we effectively know what this current is as well, because GM is defined in the problem statement, 4 millisiemens. So we know that the current flowing down here is simply 4 millisiemens times 2.941 sine 10t volts. So the question then is, how do I solve for the output voltage? Anybody have any ideas? Yes, sir. So they are in parallel, I believe, so I can combine them. Okay, so we can combine them into a single equivalent resistance. So what that circuit, the right-hand side of the circuit, will look like is we have this current source, GM, V pi, both of which are known. Our equivalent resistance, which I'm going to ask you guys to calculate in a moment. And then here is our output voltage, V out, as a function of time. So how do I combine resistances in parallel? Okay, so I add the reciprocals. So 1 over 100K plus 1 over 5K. What do I do to that sum? Yeah, so I take the reciprocal of that. Alrighty, an alternative way to do it, and it only works when there are two resistors, would be I take the product and I divide by the sum. This only works when there are exactly two resistors in parallel, the bottom expression. Okay, so I want to be really, really clear about that. Yeah, so either way is going to give us the exact same result. So let's see, 1 over 100 plus 1 over 5, that whole thing to the -1 power gives me 4.762 kilo ohms. And just for the sake of argument, 500 divided by 105 gives me 4.762 kilo ohms. So exact same thing. All right, so now that I know the equivalent resistance, how do I get the voltage drop P out? So Kirchhoff's current law is kind of overkill when we only have one resistor, right? All of the current, GM V pi, has to flow through that resistance REQ because it's literally the only path for it to flow through. So KCL doesn't really help us because it will tell us that GM V pi is equal to GM V pi. So When I have a current and and a resistance, and I want to find the voltage, what do I use? Ohm's law, right? All right. So using Ohm's law, what is our output voltage going to be? Anybody want to tell me how to do it? All right, so the answer is 56.022 sine 10t volts. However, my answer that I have written up here is negative. Why is there a negative sign? Exactly right. The current is flowing into the negative polarity terminal. So V out as a function of time is going to be negative 4 millisiemens times 2.941 sine 10t volts times 4.762 kilo ohms, and this exactly equals negative 56.02208.457 or some crap like that. I only remember it because I did it like an hour ago. Sine 10t volts. So does anybody have any questions about the steps we took in this particular problem? So negative 4 millisiemens is this GM, right? Given to us here in the problem statement. So this dependent source, the amount of current that it is supplying is GM multiplied by our controlling voltage V pi. So this is GM, this is V pi, and over here is REQ. And the negative sign comes from the fact that that current, GM V pi, when it flows through the equivalent resistance, is going to be flowing into the negative polarity terminal and out of the positive polarity terminal. All right. Any other questions regarding the analysis of problem 3 here? Alrighty, does anybody have any other questions regarding any of the other in-class assignment problems or homework problems or really anything you want to talk about for the next 35 minutes? Yes, sir. Homework 3, problem 2. Alrighty, let's see. So this is the problem you want to look at, just to be clear? Alrighty, so give me a moment to draw it on the other thing. Let's edit. Document, insert. No, append. All right, let's see. So 2 squares. Okay, let's see. CBA. To 105.82. 158. 50. 110.75. And 200. All right. So I don't want to spend a ton of time on this problem. So would you prefer to work part A, part B, or part C? Part A, all righty. So we're looking at the equivalent resistance seen between terminals A and B. All right, so that means that terminal C, well, we'll leave this guy here for now. Okay, so I'm going to redraw this really slightly. We can kind of see a set of terminals. So effectively what we're going to do in this problem, we can see that there's an 82 ohm resistor, at least for my numbers, directly connecting terminals A and B. And so our goal is really going to be to combine the entire rest of the circuit into a single resistance that will be in parallel with that guy. So to that end, I'm going to identify all of my nodes. So in red here, this guy is A, because it's connected to terminal A. Blue will be node B. And green will be node C. And pink, let's call this guy D. Light blue, we'll call this guy E. And purple, we'll call F. And this is just the way that I like to solve problems that involve resistance combination. It helps me see connections, like particularly things in parallel, to see that they share the same colors. So one thing that I can observe kind of right off the bat is that node D connects the 100 ohm resistor and the 25 ohm resistor, and it doesn't have any branching paths off of it, which means the 100 ohm resistor and the 25 ohm resistor have to be connected in series, okay? So how do I combine those two? Add them. So 100 plus 25 is 125. So what I'm going to do is I'm going to replace this guy with a 125 ohm resistor. And then my 25 ohm resistor goes away. And I can now see that node E actually stretches all the way over here. Okay. Node F, similar situation, right? It connects the 200 ohm resistor and the 75 ohm resistor, but there are no branching paths, so that means the 275 are in series. So I could replace those with a single 275 ohm resistor. Everybody okay with that? All right, so means node F is gone. Alrighty. So now that node E takes up the entire bottom, what has changed, right? So let's look. We can see that the 125 ohm resistor and the 58 ohm resistor, how are they connected? They're in parallel because they share the green and the light blue nodes. So let's combine those two guys, right? So what is 125 and 58 in parallel? 39.62 ohms. Everybody agree with that? All righty. So I'm going to erase this guy here. So that is 39.62. Let me re-pencil in this node. What can I say, excuse me, about the 110 ohm resistor and the 275 ohm resistor? All right, so that is RAE is 110 in parallel with 275. (78.57 ohms). All right. All righty. So let's see what we've got going on here now. So node C is now a single point of interconnection between the 105 ohm resistor and the 39.62 ohm resistor, right? So that means that they're in series. And the total series resistance between node B and E is just going to be 105 plus 39.62, which is 144.62. My mental math is correct. All right. Okay. So what's the next resistor combination that I can make? I'm sorry, could you speak up, please? So the 82 and the 78.57, they are not connected in parallel because while they do share the red node, they don't share the blue or the light blue node. And they're also not in series. And so this is maybe a little bit harder to explain why they're not in series, but they're not in series because there is a branch that goes off to connect to terminal A. So look at the node B and node E and tell me which resistors are in parallel. So the 144.62 and the 50 are in parallel. Can everybody see that? All righty. So that is going to be what we're going to call, let's call it RBE prime. Somebody give me a number for that. All righty. So we're gonna erase all this junk over here. 37.15. All righty. And so what's our next combination that we can make? Absolutely, because they share node E, and node E doesn't branch off anymore, right? So that means that the 37.15 and the 78.57 are in series. So we're going to call that RBA. It's not black. And that's just 37.15 plus 78.57. And I can't do that in my head. $115.72. Alrighty, so I'm going to erase those guys. And so between nodes B and A, I place 115.72. So what's the relationship between the 82 and the 115.72? They're in parallel. So our final equivalent resistance, RAB, is 82 times 115.72 divided by 82 plus 115.72. $47.99. Alrighty, so I'm going to pop over to WebWork real quick, and I'm going to plug that in. It might tell me it's, what the heck is this? Okay. All right, I'm going to have to plug in my stupid keyboard. Picking me off. 47. Come on. No. Why isn't my keyboard working? All right, well, let's just check it then. Or it's going to be difficult because, of course, it is. Oh my God, Zoom, leave me alone. Well, WebWork or my computer, one or the other is being difficult and not accepting inputs. Let's see. What's going on here? All right, so it finally showed up. So 47.993 blah, blah, blah is the correct answer for part A for my numbers. So all of our process was correct. Since you guys are going to have different numbers, it does not bother me whatsoever that you're seeing what my correct ones are. All righty, so if we wanted to find it between B and C, which I believe is part B, it's effectively the exact same problem, but we're just moving the terminals over to the right. So the process is effectively the same. Between C and D, things become slightly different, but the process is the same. You know, identify your nodes, look at which elements are in series, which elements are in parallel, and then just make simple iterative combinations. And then redraw your circuit to help you out. All right, any other questions regarding the in-class assignments or any of the homework problems? Problem one, all right. So let me add a new sheet of paper. Is my keyboard not working? All right, well, I'll just scroll down and do it then. All righty. So homework 3, problem 1. This one, I get questions about literally every quarter. I think this is my 13th quarter in a row of teaching Circuits 1, and I have never had a single quarter where at least 2 or 3 students in it didn't ask me about this. So what this guy is a big ugly problem. It looks something like this. Let's call this guy R1, this guy R2. For the current source is the direction from left to right or right to left for the independent current source. Let's call that IS. The dependent current source is going in the opposite direction, so that's left to right, and it is 0.5 Vx. Here's resistor R4. Is the positive polarity terminal for Vx on the left or the right? All right, then this is the current I1, I2, I3, I4, and I5. Alrighty, and I'm not going to bother putting any numbers in because it's actually just going to slow us down. So you're told in the problem statement that this is a single node pair circuit. So I'm going to go ahead and prove that because it will help. So the node I've outlined here in red will be our top node. And the node I'm outlining here in blue will be our bottom node. So we're going to redraw it. Alrighty, so here's my resistor R1, here's my resistor R2, here's my current source. Now I can see in my original drawing that the tail of the arrow for the current source is connected to the bottom node, and the head of the arrow is directed to the top node. So that means the current is flowing from bottom to top, like so. Here is R3, here is my dependent source. And dependent source, I can see that the tail is connected to the top, the head is connected to the bottom. So that means it's flowing from top to bottom. Alrighty, so now Vx is connected, positive polarity terminal is connected to the top. So here's Vx. The current I1 is flowing through resistor R1 from top to bottom. So this is going to be I1. The current I5 is flowing through resistor R4 from bottom to top. So here's I5. And I2, I3, and I4 are the ones that are a little bit harder to label, so we'll talk our way through those. All right, so I2, we can see that the tail is connected to the node shared between the tail of the current source IS and the resistor R3. So that would be effectively this big node right here, which I did not mean to erase it. And it is flowing to the node connecting resistors R1 and R2 with the negative polarity terminal of the voltage attached. So that means this guy right here. So that means that this current is I2, flowing from the tail of the current source to the bottom of the resistors R1 and R3. Current I3 is flowing from the node that connects resistor R3 and the tail of the dependent current source, so this guy, and it is flowing to the node that connects the head of the current source arrow and the resistor R2. So it's flowing to this guy. So there is I3. And then lastly, I4 originates at the node with connected to the resistor R4 and the head of the dependent current source arrow, which is this guy, and flows to the tail of the current source node. So this is current I4. In my opinion, labeling those three currents is the hardest part of this problem. Everything else is simply Kirchhoff's current law and Ohm's law. So, because this is a single node pair circuit, the first thing that we are going to do is write a KCL equation that will allow us to calculate the voltage Vx that is common to all of the elements. And so I'm going to do something that might seem a little bit weird, but I'm going to entirely ignore the currents I1, I2, I3, I4, and I5 right now while I write this expression, okay? Because they're not going to do anything but add confusion. So what I'm going to do is I'm going to label the currents through all of my resistors direction down. So for instance, this is my resistor current through R1 that I'm going to be paying attention to. This is my resistor current through R2. Here's my resistor current through R3. And here's my resistor current through R4. And the reason why I'm directing them all downward is so that they flow into the positive polarity terminal of the voltage Vx, right? Because Vx is common over all of these elements because everything is connected in parallel. So my KCL expression is going to be set up in such a way that I'm setting up all of the resistors to absorb power because I know that that's what they should be doing, okay? So that's why I've just chosen arbitrarily all of those resistor currents to go down. All right, so I'm going to write an expression, Kirchhoff's current law at the top node with currents leaving being positive. All right, so how am I going to express the current that's flowing down through resistor R1 in terms of that common voltage Vx? Resistor value, I don't care about the resistor values. So I want an Ohm's law expression that relates this current that I've drawn in, I don't know, blue, green, or whatever, to the voltage Vx. Okay, that's absolutely right. What about the current flowing down through resistor R2? Alrighty, so my current source is entering the top node, so should it have a negative sign or a positive sign? Negative, because currents that are leaving are positive. So negative IS. How do I express the current flowing through resistor R3 in terms of Vx? What about the current flowing down through the dependent current source? And lastly, the current flowing down through resistor R4. Does anybody have any questions at all about this Kirchhoff's current law equation? So you do not. That 0.5 Vx is what's called a a voltage controlled current source. So the units on that quantity 0.5 are actually amps per volt, even though they're not explicitly stated. So that's a current source, and so that's why we're just adding that to it, right? So if it were a voltage, we'd need to divide by the resistor value, but because it's a current, we don't. Does that make sense? All righty. Any other questions regarding that Kirchhoff's current law expression? All righty. So now our goal is to put these currents I1, I2, I3, I4, and I5 in terms of the voltage Vx, because our equation for Vx is one equation, one unknown. So I'm going to assume that all of you guys are capable of solving that using a calculator or a bunch of algebra that I wouldn't wish on anybody. So use a calculator, please. So how can we write an expression for, let's say, I1 in terms of Vx? Somebody that isn't you because you did the whole first one. Sorry. If we have to, we'll come back to you, but I want somebody else to participate. Vx divided by R1. So I1 is Vx divided by R1, because it's the current flowing down through that resistor R1, so it should look the exact same. These two quantities are representing the exact same current, the current flowing down through the resistor R1. Alrighty, now I'm going to jump all the way over to I5, because that's the other easy one. Why does it say the control button is pressed when I don't have a keyboard attached? Alrighty. So how am I going to express the current I5, which is flowing up through resistor R4 in terms of the voltage Vx? That's correct. It's negative because, as we've discussed previously, it's flowing into the negative polarity terminal of the voltage Vx. Alrighty, so now here's where things get a little bit more difficult, okay? So we're going to be applying Kirchhoff's current law at what I'd like to call a subnode. And what I mean by that is it's not the full node across the bottom or the top. but a small portion of it. And the reason we're doing that is because the current I2 doesn't flow into or out of the bottom node. It's flowing in the direction of the bottom node, right? Similarly, the current I4 isn't flowing into or out of the bottom node, it's flowing in the same direction as the bottom node. And I3 is flowing in the same direction as the top node. So we're gonna have to apply subnodes, alrighty? And so what that means really is we're gonna just apply the current going in equals the current going out relationship for these guys. So for I2, excuse me, the most simple way to do it would be I2 is the current flowing in, this current in green, and this current in green are the current flowing out of this node that I've circled in green. Is everybody okay with that? Okay, so we know what the current flowing in is. I2. So how are we going to express the current flowing up through the resistor R2 in terms of Vx? Yes, because it's flowing into the negative polarity terminal. That's correct. What about the current flowing up through resistor R1? Negative Vx over R1. All right, so we've got an equation for I2 just using Kirchhoff's current law. Now let's look at I4. I4 is another easy-ish one. So there are multiple nodes or subnodes that we could do this at. And what I mean by that is we could do it here. And so we could say that it is going to be the sum of these two currents, where this current in blue is actually this current plus this current, where this guy is this current plus this current, et cetera, or we could just call it I2. So I'm not going to do that because that's probably the hardest way to do it. I just want to let you guys know that you can absolutely work this problem choosing the other relationship than the ones that I'm doing for every single one of them. So, you know, at this subnode, we said that I2 was positive. We could have set up the KCL equation at this node that I've circled in blue and still written an equation that will work. All right, so the easiest route to do here is to say that the current I4 is leaving the node that I've circled in blue, and that this current and this current are entering. So we would have I4, the current that's leaving, is equal to the current flowing down through the dependent source, which is what? 0.5 Vx, all right. And then somebody else tell me what's the current flowing down through the resistor R4. Plus Vx over R4, absolutely right. And that's it. And so lastly, we have the current I3. And for this one, the relationships are effectively equally as ugly. So I'm just going to pick one, this one, okay. So I3 is leaving, this current is entering, this current is entering, and this current is entering. Yeah. Well, actually, drawing it with a curve like that makes it seem weird, like I'm going to count it twice, because it only flows up and down through that branch. So this will be a little bit more clear. All righty. So I3 is equal to, what's the current flowing up through resistor R3? That is a B, not an R. What is the current flowing up through the dependent source? All right. And lastly, what is the current flowing up through the resistor R4? Negative Vx over R4. So we have used Kirchhoff's current law and Ohm's law in order to express all of those loopy swoopy currents in terms of that common voltage Vx, which we were able to determine just by using Kirchhoff's current law. So now you have a set of equations that are easy enough to do. And since we didn't use any numbers, they're applicable to all of you. Alrighty, any other questions regarding, we're actually 3 minutes long, but I don't mind staying if anybody else has any questions or anything like that. If nobody, oh yes, sir. Sure. Why is it wrong that your voltage is negative? You need to change the direction of the current, right? Voltage is negative, it would mean that you would need to change the polarity of the voltage. But if the voltage already has a polarity assigned, there's nothing you can do about it. Mm-hmm. You chose the opposite direction for what current? Okay. So you chose entering the top node to be positive. So, but did you choose your resistor currents as all down or all up, or what did you do? So if you did, okay, so here's the issue, and I'll try to squeeze it in here. So let me erase some of this stuff. So the polarity of Vx is what the polarity of Vx is because it's defined in the problem statement. So we don't have any room to do anything about that, okay? Now, we do absolutely have a choice as to the direction that we define all of our resistor currents, okay? So, if we chose them all down again, so that the current is flowing into the current through each individual resistor is flowing into the positive polarity terminal of Vx. So just exactly like what we did earlier. But now we chose to do KCL at top, currents entering have a positive sign. We would have negative Vx over R1 because it's leaving, minus Vx over R2, plus IS, minus Vx over R3, minus 0.5 Vx, minus Vx over R4, and all of that is equal to 0. So it's the exact same expression that we had, but it's multiplied by a factor of -1. It's not going to change our answer for Vx at all. If instead we we chose don't need that one. The current's all flowing up. Our expression would not change one bit. And the reason why our expression will not change at all is because this current is flowing into the negative polarity terminal. So the current flowing up through the resistor R1 is still negative, or it's negative Vx over R1. Current flowing up through resistor 2 is negative Vx over R2. We have a negative sign anytime the current is flowing into the negative polarity terminal when we're talking about a resistor. Now we could go just completely wackadoodle and not have all of our resistor currents in the same direction, but we'll find out. So let's say that we make this guy down and this guy down, but the other two up, okay? But we're going to use the exact same convention. Currents entering are positive and currents that are exiting are negative, okay? So this current flowing through the resistor up through the resistor R1 is going to be negative Vx over R1 because the current's entering the negative polarity terminal, right? So it's positive negative Vx over R1, which is negative Vx over R1. For the current flowing through the resistor R2, it's going to be Vx over R2, but because it's leaving, it will be negative Vx over R2. Current Is is entering, so it's positive. The current flowing down through resistor R3 in terms of Vx is Vx over R3, but because it's exiting, we would assign it a negative, so it's negative Vx over R3. Then we're going to have minus 0.5 Vx, and then lastly, the current we're going to have positive negative Vx over R4 equals 0. So it does not matter what direction we choose for our resistor currents, whether we are choosing entering as positive or exiting as positive, we're going to get the exact same result as long as we're applying Ohm's law correctly, in as much as if the current is entering the negative polarity terminal, it needs to have a negative sign, and if it's entering the positive polarity terminal, it should have a positive sign. So we can mix, match, do whatever the hell we want to make it as easy or as complicated as we want to, but you should still actually get the same result regardless. So if using your numbers, Vx happens to be negative, really nothing you can do about it. It's just, it is what it is, based on all the other things influencing stuff. Exactly right. And you just need to make sure that when you substitute in Vx to all these other relationships, that you're using the negative value, regardless of what the sign. So in this case, that would mean I1 would be negative and I5 would be positive, because positive, negative some quantity gives us a negative number, and negative, negative some quantity gives us a positive number. So it all works itself out in the end to be correct. Any other questions or anything? It's 2:30 now, so we're a full 10 minutes long. So if you could please grab a towel and at least one person wipe down the table that you're sitting at. Thank you, and I'll see you guys on Wednesday, where we talk about linearity and superposition, and also do another lab assignment. And the lab assignment for Wednesday, it's a breadboard, a couple of resistors, and just using a multimeter to take some measurements. So potentially, if we ran out of time, you guys could literally do the lab at your home with the kit and your multimeter from Engineering 121 or 120 or whatever.